Imagine you have been playing a video game for 2 hours. You are not particularly enjoying it anymore. You are not relaxed. You are not having fun in any conventional sense of the word. But you cannot stop. Something keeps pulling you back to the screen, back to the next match, the next loot drop, the next rank. You tell yourself 5 more minutes. You have been saying that for 45 minutes. Here is what most people assume in that moment. They assume it is a personal failure, a lack of willpower, a character flaw. What the neuroscience actually reveals is something far more precise, far more deliberate, and honestly far more disturbing. What is happening inside your brain in that moment was not accidental. It was engineered, and the blueprints were drawn up decades before the first video game was ever made. This is the story of how your brain's reward architecture was mapped, studied, and then systematically exploited by one of the largest entertainment industries on Earth. Not through manipulation in the crude, obvious sense. Through the application of some of the most rigorous behavioral science ever conducted. The scientists who figured out how to hijack human motivation did not work for game studios. Some of them worked with pigeons. Let us start with the foundation because, without understanding this, nothing else in this video will make full sense. In the 1950s, the American psychologist B.F. Skinner conducted a series of experiments that would, decades later, quietly reshape the architecture of nearly every major video game ever built. Skinner placed pigeons inside controlled boxes and taught them to press levers for food pellets. He then varied the reward schedule. Sometimes the pellet came every time, sometimes after a fixed number of presses, and sometimes at completely unpredictable intervals. That last condition, the unpredictable one, which Skinner called a variable ratio reinforcement schedule, produced something remarkable. The pigeons became compulsive. They pressed the lever faster, more desperately, and crucially, they kept pressing long after the reward stopped entirely. The uncertainty itself had become the engine of behavior. Skinner was studying pigeons. He had no idea he was writing the design document for the modern video game economy. The link between Skinner's variable ratio schedule and dopamine, the neurotransmitter most associated with motivation and reward, was formalized in a landmark 1998 study by neuroscientist Wolfram Schultz. Published in the Journal of Neurophysiology, Schultz discovered something counterintuitive. Dopamine neurons do not fire primarily in response to rewards themselves. They fire in response to the anticipation of uncertain rewards. When a reward is guaranteed and predictable, dopamine activity is essentially flat. But when a reward might come, when there is real uncertainty in the outcome, dopamine release spikes dramatically. In experiments comparing fixed reward schedules to variable ones, variable ratio conditions generated up to 4 times more dopaminergic activity. 4 times. What this means in practical terms is that your brain is not wired to enjoy receiving things. It is wired to crave the possibility of receiving things. And this distinction, seemingly academic, is the single most important fact you need to understand about why modern games hold attention the way they do. A loot box does not need to contain anything valuable. It needs to contain the possibility of something valuable. A ranked match does not need to be winnable. It needs to feel winnable. The chest, the crate, the pull, the drop, none of these are rewards in the functional sense. They are dopamine delivery mechanisms dressed in reward clothing, and they were built that way consciously by people who had read the same literature you are now hearing about. David Zendel and Paul Cairns published an analysis in Royal Society Open Science, confirming that loot box mechanics directly replicate the variable ratio reinforcement structures identified in gambling research. This is not a metaphor. The structural identity between a slot machine and a loot box animation, the spin, the pause, the reveal, is functionally exact at the neurological level. But the manipulation does not stop at loot boxes. There is a more subtle mechanic at work, one that is arguably more powerful, and almost no one talks about it. It is called the near-miss effect, and it was first documented rigorously in gambling research by Luke Clark and colleagues at Cambridge, published in the journal Neuron in 2012. A near miss is not a loss. It is the experience of almost winning. The slots that show 2 jackpot symbols and stopped just before the third. The battle royale where you finish second place, eliminated in the final circle. The ranked match where your team loses by one objective in the final 30 seconds. These are not neutral losses. They are neurologically distinct from ordinary losses, and the distinction is alarming. Clark's research showed that near-miss events activate the brain's win-associated reward circuitry, the same circuits that light up during actual victories, despite the outcome being objectively a failure. The brain interprets a near miss not as a loss, but as evidence that a win is close, that the next attempt is more likely to succeed. This is factually incorrect. In random systems like slot machines, every pull is statistically independent. In video games, a second-place finish does not predict a first-place finish next round. But the brain does not process probability that way. It processes pattern, and near misses feel like patterns, even when they are not. What makes this particularly consequential is that game designers apply it deliberately. Ranked matchmaking loss screens, showing how close the player was to ranking up. Gotcha pull animations, pausing dramatically on rare tier symbols before resolving to a common item. Final circle eliminations framed with replay cameras and near-win statistics. These are not interface design choices made for clarity. They are psychological architecture. They keep the player in a state of perpetual almost, and the almost is more motivating than the win itself. Now, at this point, a reasonable person might ask, if this is so powerful, why is not everyone addicted? Why do most people who play games regularly still maintain healthy, functioning lives? This is where the science gets genuinely complicated and where the mainstream cultural narrative about gaming has done serious damage. The World Health Organization classified gaming disorder as an official mental health condition in the International Classification of Diseases, 11th edition, in 2019. That classification generated enormous media coverage and a predictable wave of moral panic. What the coverage largely omitted was the actual prevalence data. A large-scale study conducted by researchers at the Oxford Internet Institute, led by Andrew Przybylski, and published in the Journal of Psychiatric Research, examined over 1,000 gamers against clinical criteria for gaming disorder. The percentage meeting actual diagnostic threshold, somewhere between 0.3 and 1%, not 30%, not 10, less than 1. The neurological risk mechanisms documented in this video are real, but the incidence of clinically significant gaming disorder is, by rigorous measurement, far lower than media coverage implies. More importantly, a 2017 study by Przybylski, Weinstein, and Murayama in the American Journal of Psychiatry, extended by Vore and colleagues in Royal Society Open Science, found something that fundamentally reframes the entire conversation. The type of motivation driving gaming, not the hours played, was the primary predictor of whether gaming became problematic. Players who gamed because they found it genuinely engaging, because it satisfied their need for competence, autonomy, and social connection. Those players showed healthy relationships with games, even at high hours of play. Players who gamed to escape external pressure, whether from school stress, parental expectations, social comparison, or occupational burnout. Those players showed the profile most associated with compulsive use. In other words, the game itself was rarely the root cause. The surrounding environment was. This does not absolve the industry of engineering compulsive mechanics. It does mean the conversation needs to be more sophisticated than it currently is. But let us not let the industry off the hook, because there is another mechanism worth examining in detail, one that operates at a structural level inside nearly every competitive game played by hundreds of millions of people. The ELO rating system was developed by the Hungarian-American physicist Arpad Elo in 1978, originally for chess. It is an elegant mathematical model that attempts to estimate a player's true skill level based on win and loss outcomes relative to opponent's strength. Over the decades, it has become the foundational algorithm behind competitive matchmaking in chess, League of Legends, and most major, ranked multiplayer systems globally. It is presented to players as a measure of skill. What it is, functionally, is a psychological treadmill. Here is how it works. The system is designed to keep your win rate near 50% regardless of your skill level. If you win consistently, You are matched against stronger opponents until you lose consistently. If you lose consistently, you are matched against weaker opponents until you win consistently. The result is that every player, at every rank, perpetually experiences the same emotional volatility, the same ratio of wins to losses, the same proximity to either promotion or relegation. This was analyzed in depth by Thorgray Pell and Ralph Herdrich in their True Skill paper published by Microsoft Research, which examined the psychological implications of skill-based matchmaking architectures. The conclusion was direct. These systems do not measure your improvements. They measure your rank relative to the current player pool, which shifts with the population. You can become objectively better at the game, and your rank can remain stationary for months. The player experiences this as a personal failure. The system has actually performed exactly as designed. It has kept you in a state of perpetual near success, permanently feeling one rank away from your true level, permanently motivated to play just a few more matches to break through. This is the near-miss effect applied at a systemic, months-long scale. It is arguably one of the most effective psychological retention mechanisms ever built into an entertainment product, and it interacts with another well-documented cognitive bias, loss aversion. In 1979, Daniel Kahneman and Amos Tversky published prospect theory in the journal Econometrica, one of the most cited papers in the history of behavioral economics. Their core finding: losses feel approximately twice as painful as equivalent gains feel good. Losing $20 hurts roughly twice as much as winning $20 feels pleasant. This symmetry is not rational. It is hardwired. Juho Hamari and Vili Ledonverta applied this framework directly to game economies in their 2010 paper in the International Journal of Business Science and Applied Management, demonstrating that in-game item loss triggers measurably stronger emotional responses than item gain of identical objective value. This is why streak protection systems exist in games, why comeback mechanics feel so satisfying, why losing a character you spent 40 hours developing in a roguelike feels genuinely devastating in a way that contradicts the rational understanding that it was never real. The brain does not distinguish between real loss and virtual loss at the emotional processing level. Game designers know this. It is a documented, referenced, studied fact. Now, here is the point in this video where the story shifts. Because not everything discovered in this research is a warning. Some of it is genuinely remarkable in ways that cut against the standard narrative entirely. In 2014, neuroscientist Simone Kuhn and colleagues published a study in Molecular Psychiatry, part of the Nature Publishing Group, in which participants played Super Mario 64 for 30 minutes a day across 2 months. Brain scans taken before and after showed measurable increases in gray matter density in the right hippocampus, the prefrontal cortex, and the cerebellum. These are regions associated with spatial navigation, strategic planning, and motor coordination. These regions also happen to be among those that show the most significant atrophy in patients with depression, post-traumatic stress disorder, and schizophrenia. By Kuhn's team proposed, carefully and with appropriate scientific caution, that gaming might theoretically serve as a low-cost neurological intervention for populations where these regions are compromised. 10 hours of action gaming produced changes visible on a brain scan. That is not a small finding. The American researchers C. Sean Green and Daphne Bavelier, in work published in Nature in 2003 and replicated with expanded methodology in 2012, demonstrated that action game training accelerates perceptual learning, the speed at which the brain integrates and categorizes new sensory information, by approximately 20% compared to control group. The effect was robust enough that the United States Army Research Laboratory, in a technical report designated RLTR6120, incorporated commercial off-the-shelf action games into cognitive training protocols specifically because the transfer to real-world target identification speed was faster than purpose-built military simulator. The United States military chose commercial video games over their own custom tools because the science showed the commercial games worked better. And then there is the flow state, which may be the most underappreciated neurological phenomenon in the entire field of game science. Mihaly Csikszentmihalyi, the Hungarian-American psychologist, first formally described flow in the 1990s. A state of complete cognitive absorption in which a person is so immersed in an activity that self-consciousness disappears, time distortion occurs, and performance often reaches its individual peak. Csikszentmihalyi documented flow in artists, athletes, surgeons, and musicians. He also noted it in gamers. Though the field largely failed to take that observation seriously for another decade, the neurological correlate of flow was studied by Matthias Ulrich and colleagues in a 2014 paper published in Neuroimage by Elsevier. Using neuroimaging during experimentally induced flow states, the researchers found something that challenges how most people think about gaming. During flow, activity in the prefrontal cortex, the region of the brain responsible for self-criticism, conscious risk assessment, rumination, and time awareness, is measurably suppressed. The brain essentially pauses its internal editor. The pattern of activity observed was neurologically indistinguishable from states documented in experienced meditators and in jazz musicians during improvisation. Gaming, at its most absorbing, induces a measurable, altered state of consciousness. It is just that the people experiencing it are staring at a monitor, so the cultural framework for recognizing it as such does not exist. This has implications that extend beyond gaming. If flow is therapeutically beneficial in meditation and in music, which clinical literature increasingly supports, then the question of why it would not be therapeutically significant in gaming becomes harder to dismiss. The environment is different. The neurological signature is the same. But there is one final finding in this body of research that deserves its own consideration, because it may be the most structurally important of all, and it operates at the level of identity rather than neurology. The word gamer as a self-identified demographic category did not exist in mainstream usage before approximately 1993 to 1994. Adrian Shaw, in a 2012 paper published in New Media and Society, traced the construction of gamer as a cultural identity through gaming magazines, early internet forums, and retail marketing campaigns. The term was not organic. It was manufactured primarily as a marketing tool to create brand loyalty, justify premium pricing, and build a captive consumer demographic. Mia Consalvo's 2007 book Cheating, Gaining an Advantage in Video Games, published by MIT Press, examined how this identity construct affected consumer behavior and in-group defensiveness. The implications, once you look at the identity psychology literature, are significant. When a person adopts gamer as a core identity label, rather than simply as a description of a hobby, their susceptibility to in-group marketing increases, their spending behavior on gaming products measurably increases, their emotional investment in defending gaming as an activity increases, and their resistance to reducing game time increases. All of this is documented. You are not just buying a game. At the identity level, buying the game is buying membership in a community, and the community was built specifically to sell you the game. None of this means gaming is malevolent. It means gaming is an industry, with incentives, with behavioral science departments, with engagement metrics that determine whether a product survives financially. The tools it uses are the tools of every attention economy in the modern world. The difference is that gaming applies them with unusually precise knowledge of the neurological substrate, and with unusually direct access to users across thousands of hours of engaged interaction. The esports data may be the best illustration of this reality. A study commissioned by ESL, the Electronic Sports League, and corroborated by research from Deutsche Sporthochschule Köln, measured cortisol levels in professional esports competitors during competition. Cortisol is the body's primary stress hormone. Resting baseline is approximately 100 units. Formula One drivers during races and professional soccer players during high-intensity matches typically average 500 to 600 cortisol units. The esports players sitting in chairs, looking at screens, showed identical numbers. The physiological stress response of competitive gaming is equivalent to motorsport without the motor. The body does not care that the stimuli are virtual. The threat response architecture it is running is the same one that evolved to handle physical danger. These are the systems inside you right now, and the people who build the games you play know them better than most players ever will. The picture that emerges from all of this research is not simple. It is not a condemnation and it is not a vindication. It is a map. Gaming can grow gray matter and accelerate cognitive function. It can also exploit dopaminergic anticipation cycles and loss aversion in ways that are functionally equivalent to casino design. It can induce meditative states, and it can engineer indefinite engagement through algorithmic near misses. The technology is neutral in the way that any technology is neutral, which is to say, not very, in practice, when the incentives of its builders are understood. What the science asks of you is not abstinence. It is legibility, knowing what is actually happening when you cannot put the controller down, knowing what the loot box animation is actually doing to your dopamine system, knowing that the rank you are grinding for is mathematically calibrated to keep you perpetually almost there. That knowledge does not remove the pull, but it changes the relationship. You can want the hit and still understand you are being given the hit deliberately. That distinction matters, and it is exactly the kind of thing that rarely makes it into the conversation. If you found this video genuinely useful, the work that goes into researching and structuring content at this level takes serious time. There is a lot more in this space that deserves to be examined with the same rigor. If that is the kind of content you want more of, you know what to do.